Welcome to our BNS on Aerospace and Defense podcast series. I'm Pat Hindle, Media Director for Microwave Journal and Signal Integrity Journal, and I'm here with our hosts, Brian Goldstein, President, Analog Devices Federal, and Vice President, Aerospace and Defense Group at Analog Devices, and Sean Darcy, Senior Director of Aerospace and Defense at Infineon. Welcome, guys.
Thank you, Pat, and welcome to you, John.
Yeah, we have a special guest with us today, John Park, Product Management Group Director for IC Packaging and Cross-Platform Solutions at Cadence Design Systems. Welcome, John.
Thank you for having me.
So heterogeneous integration is another hot topic that we wanted to tackle today. So we're going to delve into that topic. And in order to squeeze more performance out of smaller and smaller footprints, one solution is heterogeneous integration. But there are other solutions too, so I thought we'd compare and contrast some of those in our discussion today. And as usual, Sean will kick us off. And, we always start with, what the heck is it?
What the hell is it? Yeah. So, John, just like you and me, for one thing, we need much longer titles after our name because Brian's got us beat by about 5 minutes. So, with that being said, so let's start off with talking a little bit about heterogeneous integration. I'd like to ask you, John, why don't you start with telling us what it is? How's it different from certain things like 2.5, 3D integration, or systems on chip or system in package? Let us know a little bit about what you think it is and what it's being used at or used for.
I will give you my definition, and I've been involved with heterogeneous integration, how it's used today anyways, I think from the beginning, which was the DARPA CHIPS program, which kicked off this whole idea of chiplets. And that's where the term heterogeneous integration first started being used. And I think to a lot of people, it really means just the disaggregation of an SoC. So it really, the question, how it differs from 2.5D and 3D, it doesn't. Those are packaging technologies that integrate the disaggregated chiplets that were once part of a monolithic chip. So if you look at a monolithic chip today, and we go off and design, at 3 nanometers, 2 nanometers, it costs lots and lots of money. Of course, close to $500 million. And if you're in a market such as aerospace and defense, where you're not necessarily designing high volume products, it's impossible to recoup the NRE in those types of scenarios. So what a lot of the defense and industrial base and aerospace and defense has started looking at, who is really driving heterogeneous integration, is how can we take this very expensive die, split it into a bunch of pieces, and build those pieces at nodes that don't cost us millions and millions of dollars to design. So, especially in aerospace defense, we have high mix, right? Meaning we've got RF in there, we've got digital in there, we've got analog in there, we got all this mix of stuff, and those technologies do not scale like traditional digital logic. So it doesn't make sense to chase, follow Moore's law and chase after the latest node from a cost perspective or a technology perspective. So that to me that market says, okay, let's blow this thing apart instead of a single monolithic die. Let's build these little blocks called chiplets, and let's build them at whatever node makes the most sense for that technology. And that's where the term heterogeneous comes in, because these chiplets could be at 28 nanometer, they could be at 10 nanometer, they could be in GaN, they could be at GaAs. We don't really care. But tying it back to 2.5D and 3D, those are the technologies used to then aggregate those chiplets into an end product or a system, and some people would call it system and package. So I think a more accurate question would be, how does SIP differ from SoC? Because that's what to me, heterogeneous integration is all about. It's moving to a system on a package or in a package.
Boy, I think you gave a great visual description, and I think you also gave a great pros and cons. Certainly the pros. I want to talk about the cons. This sounds like an obvious thing to do, right? Breaking it up, going to the cheapest node that's possible, the fastest node, the right node with the right performance depending on the function. That seems like the obvious thing to do. So why hasn't it been done yet? What makes it hard?
First of all, it has been done. If you look at like multi-chip modules, system and packages, I've personally been doing this for 40 years, and MCMs were here before I got here. So that those were absolutely heterogeneously integrating things together. Back then it was full die, and today's it's chiplets. But So we have been doing this. And then for a long time, we kind of went to the system on a chip, right? It's like we have these PCBs, which represent a system, and to get improved performance and lower power and all these things, we shrink things. That's what we do. And so we follow Moore's law, and we just cram more and more onto a single monolithic chip. And you're not going to ever beat the performance of having that integrated monolithic system. So from that perspective, especially in the digital space I'm talking here, which is a lot of the commercial applications, it drove the market. It set the trends. We just kind of every 2 years we counted on Moore's law, and we kept taking advantage of twice as many transistors and lower power and all these great things. And of course, Moore's law slowing down. That's one of the reasons is the fact that we're running out of facing the limitations of physics of how we can actually scale. But the other factors coming into play is, and this applies a lot to mostly the commercial market, but we started running out of real estate on these monolithic chips. So right, we can only build things in a wafer foundry that are 856 millimeters square. So we can only fit so much functionality on that thing. And now people are building these huge SoCs. And that's another reason that a lot of companies are disaggregating is, okay, I built this, I've started putting more and more on, I can't build anymore, I can't fit any more on there. So that's another thing that's driving heterogeneous integration. That's kind of beyond just looking at the cost factor there. And of course, as we know, when we build these huge chips, they don't yield anyways, again, driving up the cost. So I will say, there are applications where heterogeneous integration makes a lot of sense. I think particularly in aerospace defense, where it's a high mix, low volume, because it is going to be, I think, a more efficient way to design products from a technological perspective as well as an economical perspective. But there certainly will be applications, in higher volume that are really digital centric that will still remain in that world of monolithic SoC design.
I have a quick follow-up definition question. You had clarified heterogeneous versus 2.5 and 3D integration and system and package, system on chip. The other question then term is chiplet. There's a lot of confusion around what is the definition of a chiplet and how is a chiplet different than what is already known as a known good die?
Great question. Comes up at every single event I go and speak at or attend. It's and there is a definition online that a lot of people are following, but I'll kind of ad lib it here. So in my view, and a lot of people's view, a chiplet is something that used to be part of monolithic chip, so block, like typically a macro, an IP block, that's been taken off that chip and formed into this, block of IP that's got a little wrapper around it, and that wrapper has a PHY that's based on UCIe or BOW or AIB. So it's got a die-to-die or chiplet-to-chiplet interface on it. It's got other I/O. They're handling things like test and driving the other signals on the design. So to me, a chiplet is a partial. And by the way, chiplet comes from dielet. The original, when people started first doing this, and I'm not going to name names here, but the original term was dielet, which is actually a more accurate representation. But chiplet seemed to catch on a little more than dielet. But it's a small part of a die that gets broken. That used to be part of this monolithic thing. That is part, but now it's being broken into functioning on its own and being designed on its own. And then the packaging is then what takes and aggregates and puts those chiplets together.
All right. So a chiplet, is it fair to say a chiplet is a known good die, but a known good die may not be a chiplet?
Correct. To me, a die is a die. It's functional within itself. Yep. So I can take a die and it has full functionality for whatever you're trying to do. A chiplet is a chiplet. It's a part of a chip that's been disaggregated and it doesn't really work on its own. It kind of relies on the interfaces to other chiplets to perform a system or subsystem.
All right, fair enough.
And there is one other small little variation to that some people are starting to also use, and that is a die or a stack of die that's designed and architected specifically to go into a package. So that would be something like HBM. So HBM, based stacked DRAM, and it's designed specifically to go inside the package, sitting right next to your GPU or CPU or whatever it is. So it's got a smaller pin pitch, it's got smaller buffers because you don't have to worry about driving these huge capacitive loads. And so that there is the slight variance that some people use to describing a chiplet.
No, excellent. I think the reason chiplet took off is it sounds a lot like a obscure type of gum that us old people remember. So
Yeah,
that's why it happened.
you can still get it. You can still get it on the beaches of Mexico. At least last time I was.
I love it. That's good to know. Hey, I wanted to ask you just another quick question there. So a lot of the heterogeneous integration you've been talking about is a lot on that sounds like on the digital side. How much of that actually applies over to analog RF type components? Is that being integrated a lot as well, or how do you see that playing out?
Yeah, so you're right. A lot of it's being done, at the hyperscalers, as a lot of people call them, to get more performance because their chips are too big to, all those types of things. And that's why you see, a lot of the standards today, like UCIe. UCIe is basically a digital to digital chiplet communication standard. So that's where a lot of it's happening. But as I said, it originated with aerospace and defense with the DARPA CHIPS program. And there is huge interest with, the defense industrial base, aerospace and defense moving forward because of the costs and things we talked about at the beginning of this little discussion here. And and you can see that, if you look at some of the programs that are out there today that are being sponsored by the US government, so we can look at SHIP, state-of-the-art heterogeneously integrated packages. That's a DARPA program, came out of Navy. Cadence participates in that. The primes for that are Qorvo on the RF side of things, Intel and Mercury Systems on the digital side of things. And so they're funded through that program to essentially stand up an onshore OSAT, that's outsourced semiconductor assembly and test house. For packaging, that's our foundry, essentially, are these OSATs. And so a lot of these government programs, obviously, are to bring a lot of things back onshore. And so SHIP the ship has sailed there. That's a program that's been out for a couple of years, funded and moving down the path. There's a new one called NGMM, Next Generation Microelectronics Manufacturing, I think and it's really about the same sort of thing, focus more on advanced materials, for example, but again, doing everything's onshore. And I want to kind of loop back to that term heterogeneous integration. So the commercial industry uses that term as I described, blowing up a chip into multiple chiplets designed at multiple nodes. That's heterogeneous. But heterogeneous integration to more and more people also applies to the materials. And we're seeing a lot of this in aerospace and defense, where it's the material is a heterogeneous material. So it's not just laminate. Maybe there's laminate with glass embedded into it, or it's, some exotic new material. So people are just now starting to use the term heterogeneous integration to also refer to heterogeneous materials within the package to, improve performance, better thermal properties, less stress, less, flex in the materials and those types of things. So NGMM is a program that's the BAA is out now. Their people are partnering up to go after that. There's of course NAPMP. There's Reshape. There's Steam Pipe. There's lots of these programs that a lot of them are part of the CHIPS Act. MGMM is before the CHIPS Act, but a lot of these newer ones are part of the CHIPS Act, which a lot of people think about. The CHIPS Act is about reshoring wafers. Well, a lot of it is, but a lot of it is also you got to package those wafers, and there's you got to package now multiple die types of applications. So a lot of the funding, some people guess about 25% of the CHIPS Act is going to fund onshore capabilities for assembly and test of multi-die packages.
I want to follow up. You were talking about heterogeneous materials. I have another definition question for you. You hear the term interposer. So can you tell us a bit what your definition of interposer is?
Well, there are multiple types of interposers. Probably the one people know the best is a silicon interposer. traditional silicon interposer, and I'm not going to name names here, probably not appropriate, but again, it's about 10-year-old technology. And of course, silicon interposers were able to become interposers because of TSVs through silicon vias. So what that meant is we could now take a piece of silicon and put a via through it and have access to both layers of design, which made it a nice material for adding for packaging, because we can put smaller geometries because it's built in a silicon foundry instead of a PCB laminate foundry. So we can go down to much finer line widths and spacing. But a silicon interposer today, in most cases, is a passive structure. So it's the silicon and then metallization of 3 to 4 metallization layers. There is no front end line of processing. There are no device layers in there. So you're not putting N wells and P wells and building devices in there. There are some more exotic cases of that, but the mainstream example of interposers are silicon. They're simply metallization. They're built in a foundry so we can get smaller geometries. The CTE is silicon, so it matches this. There's a direct match to the, if you have silicon die in your system, you have a direct CTE match. You can get smaller geometries. And so but those interposers still traditionally sit on a laminate package. So you're just creating an intermediate layer there where you can create much higher chiplet to chiplet or die to die interconnect, because you have metal wires at one micron instead of 100 microns. So that's one example. That's the most up to date. I would say probably the most commonly seen. If you Google interposer on the internet, what you most commonly see. But there are other interposers that are coming online. People use this term, an RDL interposer, and that's based on a thin film polyimide. So it's kind of in between. It's cheaper. There are no TSVs, which makes it cheaper because it's being done on a thin film laminate. And so you're able to get close to the geometries for the die-to-die interconnect that you would see on a silicon foundry, but you're not, breaking the bank with these very expensive silicon interposers. So there's those RDL interposers. There's now some interposers that have embedded bridges in them and things like that. But the basic term of an interposer to me is to create the die-to-die, a much tighter density for the die-to-die interconnect or chiplet-to-chiplet interconnect. You still have to do the RDL out to the package to, make it compatible with the PCB it's mounting onto, and that's typically transitioned down through a laminate BGA or LGA type of package.
Great, that's really.
So I did Google it, and it's actually comes from the root word interponere. Just so you guys had that knowledge.
Thank you.
Nice. Hey, so let me ask you a question, kind of change gears a little bit. So tell me what are some of the challenges, how you do simulating and design solutions for heterogeneous integration? Can you tell us a bit about that, your experience there?
Yes, it's harder than anything else anyone's done. And that's because what you're really doing is we have these tools in EDA, that's where I come from, where we have tools for designing systems. That would be PCBs, MCMs. We do things like signal integrity, and those are well-established tools. And we have tools on the die side where we do, on the digital side, we do static timing, and we work in sub-nanometer levels, and we have, billions of connections, billions of transistors. And these are traditionally two separate tools, sets of expertise, separate. You didn't say use workflows, but they're separate workflows. I know I'll get dinged for that, but that's what you have. And now with heterogeneous integration, boom, those two things are coming together. So if you had 10 tools for die design, 10 tools for system level design, you might now have 18 tools that are part of your design flow, because you're combining and converging the needs of what you still do, on the chiplet that has to do with die design, but what you now need on the systems side. So let me give you an example. So I designed monolithic chips a long time ago. I never heard the term signal integrity when I was in that world, because it's all about timing in the digital world. That's all you think about is your timing paths and STA closure and all those types of things. And you still need that when you're designing that chiplet. But now when you take that chiplet and integrate it with 5 other chiplets, and you have to do the compliance check between each of those chiplets, that's a signal integrity problem. So I'm monitoring, transmit to receive, through some interconnect channel, and I look at the eye diagram and I got to make sure there's not too much noise or jitter causing the eye to collapse. So as a, I have to know the stuff I did as a die designer, but I now have to know what signal integrity is so I can sign off on the compliance of that. That's one example. Another example would be if you're a package designer designing laminate substrates for the last 30 years. And it's a very informal manufacturing process. Some board house does the laminate for you. You get the substrates from Japan or whatever, but it's a very formal, kind of informal sort of process versus designing a chip where I have a very formal process of signing off on DRC and LBS to make sure that that GDS can be manufactured cleanly. So packaging, that people didn't know anything about that. Now they have to. Now their packaging materials are being, the packaging substrates being built in a silicon foundry. So they get rule decks to say, this is what you need to sign off for DRC. This is what you need for LBS. And so, there's learning on both sides, and the convergence of both tools has caused what it's really forced people to look at is to put more time and effort into building a design flow, because that's a competitive differentiator now. If you have a better flow than your competitor that allows you to get to the design done in 3 months instead of 5 months, there's tremendous value in that, and a lot of people are starting to recognize that. There are other things that come into play. There's something that the industry calls system LBS. So it's a little different than die level LBS. You're now at the system level. You need a tool that says, okay, are my 8 chiplets stacked correctly, aligned correctly? Do they connect, chiplet A to chiplet B to chiplet C? Is all that system level interconnect correct? In the past, we used, with MCMs, if I had a 4-die MCM, I had 5 spreadsheets, one of the pinouts of the 4-die, one of the BGA or the packages going on. And I sat there with another engineer and I said, die 1, pin 1, does it connect? And they'd go over to the other spreadsheet, and it was a manual check across spreadsheets. And sure, you can do that, if you have 50 pins, but these designs today are not 50 pins. So there's now this new requirement to formally sign off on that system level LBS. There's lots of other challenges that come to play, a lot with capacity. As you imagine, you're putting more and more stuff with higher density together. When you put things closer together, you have all kinds of thermal problems, which of course is tied to power. How do you get to the power there? Now it's too much power. You get things overheating, causes stress because we have multiple tiers of packaging here. There's CTE mismatches in a lot of these. They're bigger than they've been, so you start to get warpage and all kinds of other things that come into play that have to be accounted for. So I think a lot of people, in my opinion, that especially if you're an ex-die designer moving in this world of packaging, you thought initially, is this going to be easier? It's not. It's harder for everybody. It's harder for the die designers. It's harder for the system designers. And it's a big requirement, of course, on the EDA providers, which we are, to create more integrated. Some people, especially in aerospace and defense, call it co-design, where I can concurrently design, chiplets with the packaging, with the PCB, looking at the thermals and looking at the SI and looking at timing and all these different, multi-physics sorts of scenarios.
How about
I can go on for about another 2 hours on that topic, but that's just an idea. Some of the.
I had a question. We've talked about a lot of the pros, and we've also talked a lot about the difficulties with simulation and thermals. How about electrical performance? Is there any trade-off in terms of electrical performance in doing a system on chip as opposed to disaggregation? And what kind of things do you need to worry about performance-wise when you start breaking things up?
So it's a great question. So typically, from a pure performance perspective, when you go disaggregated or into heterogeneous integration and it's 2-dimensional, there's going to be a potential performance impact because things are farther apart and blocks are separated with IO buffers instead of just a wide bus, a metal bus going through there. So that's in the kind of in the 2-dimensional world. That's just, you have to deal with that. And the other things that we talked about that are positives have to outweigh the negatives there. But when you go into 3D, that all changes, right? So you have this big monolithic chip, right? And 2-dimensionally, it's like a city block, right? How much can you fit on that city block if you have single story homes? Not a lot. Well, what if those single story homes start becoming, 6-level hotels or things like that? The amount of people you can cram in there is tighter. And the people don't have to be on the edge of the city. They can come into the core of the city. So what we see commonly today in 3DIC or 3DHI is people take L3 and L4 cache on a digital chip that's far away. It's out on the edges, and they take it off the edge and move it directly above the processing logic in a 3D stack. So, and then there's just a connection through a wide bus through hybrid bonds. So in that case, you can actually see improved performance. And there are papers out there talking about the cadence tools and the performance increases and the thermal benefits, latency, all bandwidth, everything associated with that. There are some, plenty of documented examples of that type of stuff.
With an advantage in the RF world, if you use GaN for the high power, silicon for the control, if you use the best, material for the function,
Sure.
you get advantages in performance.
Yep.
I want to back up on something. You mentioned, some of the challenges of power. How do you address those type of challenges in heterogeneous integration? A lot of the chiplets and everything else. Tell me a bit about how you power these type of systems, right?
Yeah. So you power similar to so we have to look at power. So power starts on the PCB, right? That's where the VRM. That's where you're getting the power, and the power gets sucked through the package. That's always been where it is. And the package distributes, from the package onto the die. And now it's just multiple dies or multiple chiplets that you're distributing the power to. What a lot of people are looking now to improve power delivery, especially as we are moving things across different tiers and flipping things up and upside down and all over the place, is how you deliver power from the backside of the chiplet or backside of the die, right? So now there's technology where the power mesh doesn't have to be up on metal layer 11. It's actually right underneath the die delivering power that way. But it's power and thermal are, of course, tightly coupled together. And what's really changed from an EDA and a design perspective with power and thermal as we move to these 3D-HI systems is people want to do that. We hear this term shift left in EDA all the time, which typically means don't do your design and then send it off to someone to analyze SI or power or whatever, just to find out it's wrong. That's a little too late. Move it into the layout tool. So the layout tool person can say, oh, while I'm doing the layout, this is what's going on. So we've done that in EDA, but that's not good enough. In 3D-HI, you actually have to start doing the power planning, the thermal planning before the place and route. It's too late at the place and route stage for a lot of these things. So one of the things that's a new tool in the world of 3D-HI is an aggregation tool. So it's basically a system level planning tool where you bring all the chiplets into, and they can be black box representations, full left depth. They can be in multiple levels of development. You bring in the packaging, you bring in the PCB, all to this world, into this common platform. And from inside that platform, I'll give you an example. What the cadence tools do is I can mock up a chiplet and say, okay, I think I'm going to dissipate this amount of power, or we have a simple language that says, the northwest corner is going to dissipate this much power, the southeast corner this amount. And so we can kind of, based on our knowledge of what that chip or chiplet is going to look like when it's done, we can mock things up, start stacking them. And what we don't want to see is hotspots overlapped with each other as we stack them, because then we get this chimney effect and the whole thing's going to blow up. So what we want is these hotspots offset from one another. And so that you can't do that at place and route, because if it's 3 different dies, there's 3 different people, that interaction of bringing it back and forth is too cumbersome. So we do it in the planning stages based on a little bit of knowledge about those chiplets. We can start planning, where the hotspots need to be based on the order of the stack up, or whether they're face to back placement or face to face placement, all these different scenarios. So if you ask anyone that's moved to 3D-HI, you ask them what the toughest 3 problems are, they're going to say number 1 thermal, number 2 thermal, number 3 thermal. It's that thermal is that much of a challenge when you go to these 3D stack types of applications. It's because even if you're put a something like a DRAM that's not consuming a lot of power, and you put that on a logic die, the logic die is going to heat up that DRAM out of its operating temperature, right? 95 degrees C or whatever it is. Once that thing heats up, it doesn't work anymore. So you have to look at it holistically as you start, integrating these multiple chips or chiplets together, and even a side by side, but certainly in a vertical stack.
Hey, John talked about shifting left and didn't mention workflow.
That's right. I like
Hey,
it.
good for you.
That was really good.
I had another question. I like to ask the questions where there's all the confusion, and the other confusion is around the digital interface protocols. You started listing off a few earlier. Is there a standard? Is there still debate over the standard? And do the standards cover, all the different situations right now? And what is the state of the standards? Can you talk about that a little?
Yeah, good question. So let's go back to DARPA chips, which again, I think kind of started a lot of this. The vision of the program manager for DARPA chips really had two things he wanted to accomplish. One was to create a library of chiplets that, just like on a PCB, I can open an Aero catalog, grab my 30 parts, add my special FPGA or whatever, put it together, I have a unique system. You can't, that part of it, that library of, consumer off-the-shelf chiplets, that technology is possible, but it's a business case. So let's put that aside for now. The other goal that Dan Green wanted to achieve was a standard for die-to-die communication. And so that's where we started hearing AIB, which of course came out of Intel. Intel made that license free, and that was kind of the start. But we've, kind of moved on. There are a couple of different standards leading the way. UCIe, I would say by far looks like it's going to be the clear winner. Cadence, who's also an IP provider, we're all in with UCIe. We're a believer in that. I think pretty much everybody is in the digital space. It is primarily a digital type of application. There's also BOW that comes out of Open Compute, bunch of wires is what it stands for. There was one I think announced over the last couple of weeks by I think the company Zero ASIC. That's a universal memory interface. So UMI is what they call that. So I think we've made a lot of progress in standards for die-to-die, chiplet-to-chiplet communication. The thing that often people don't think about is what packages are going to use, right? So we've blown everything apart. Packaging has to bring it together, and we have a million ways of packaging it. It's the Wild West. There's literally hundreds of ways I can package these things together, and so that makes it challenging to just say I'm going to have only one standard, and it's going to work across laminates, silicon, 3D stacks. It's going to work across, long range, short range, all these different applications. It's really hard to have a single interface for that. So I don't know if there will ever just be one particular interface. Of course, you have to integrate, the digital with the analog and the analog with the RF, all these other things where there are still, virtually no standards around that. So I think we've made a lot of progress in standards for how we communicate on the digital side between chiplets and memory. But there are, I don't personally believe there's going to be one standard that applies to every single package. If you look at it, the pin pitch, simple thing like that. If I'm doing a laminate package, my pin pitch is going to be 130 microns, 125 microns. If I'm doing an embedded bridge or a silicon interposer, I can go down to 35 microns, right? So the pin density goes up, and I think that's going to cost a little bit more. But how do I, design an interface for all these? What is the Wild West? How do I, have that much coverage? And the good thing about UCIe is it is designed to work on what's called standard packaging and advanced packaging. So it will work with laminate, will work with silicon. You can get a PHY that, it's based off a 130 micron pitch, one that's based off a 45 micron pitch. So there is some flexibility in some of these standards that is coming out. But, I look at it a lot of times like PCBs, and there is no one standard for PCBs, right? We have PCIe and MIPI and, DDR4, and we have all these different types of standards. So I think something similar will happen here.
So hey, I want to switch a little bit of gears here. Tell me a bit about Does AI and high performance computing change which solutions, are better, SOC versus heterogeneous integration? What do you think there?
Yeah. So, if you look at, a lot of AI is driving a lot of this advanced, more on the advanced packaging, the silicon interposer side, the 3D stacking. I'm not going to name names, but there's some companies out there that are announced products where they're in that AI ML space, right? So a lot of that's about memory bandwidth. And so it's bringing HDM. If you look at how we access DRAM in the olden days, we had side-by-side DRAM placed on these little DIMM cards. They were in connectors on the PCB. You had an interconnect going across the PCB up into a package, through the package parasitics onto some processor. Okay, horrible memory bandwidth. Now we started, okay, let's make this better. We started doing package on package. So we put stack of DRAM on the processor, but you still had to go through these, package vias types of things. And if you look at where we are today, we're at, let's take those DRAM, let's stack them 3D, and let's put them right, 3 millimeters away from the processor on the silicon interposer. So that huge long interconnect path is now down to a little, 2 millimeter, 3 millimeter connection. So all the parasitics that were involved and the delay and latency and all that. So we've made a lot of progress in that space, and a lot of that's driven by the high performance compute, the AI ML applications. And it's now the point where this all kind of is leading up to where we're taking full wafers of processing logic and DRAM and stacking a full wafer on top of another wafer. Okay, so that's a very exotic. You have to have obviously a lot of redundancy in a circuit like that, but the performance is incredible. Thermal, these are liquid cooled systems, so these are not going to be something that is in your cell phone or anything like that. These are going to be in server farms that are doing a bunch of AI ML learning types of applications, and those are out there, and they are definitely pushing the 2D 3D packaging space. Are they pushing chiplets yet? Depends again on your definition of chiplets. To me, they're more pushing the state of the art in 2D, 2.5D and 3D packaging to get a lot of that. But you will see some a common example is I/O are another thing that don't scale as easily as the rest of the digital circuits. So things like high-speed SerDes, why do I go do that at 3 nanometers, or is it going to cost me lots and lots of money? Let's keep that at 10 nanometers. So you'll see some cases where things like high-speed I/O is separated into its own little chiplet and put in a package. So a long answer to, I think AI ML is impacting a lot of this multi-die, 2.5D and 3D packaging.
So I guess the other thing I wanted to ask kind of in another, market was, where do you see, what's the use here for aerospace and defense? What else do you see there as far as applications or challenges?
I see it. So I have to be a little careful here because I'm involved with some stuff that I can't publicly talk about, but so it's, as we talked about at the beginning here, in high mix systems, where you might have some high resolution image sensing, and it's coming through some phase array, and you got lots of these RF and analog and micro, all these different components coming together. That's where chiplets are great, and these advanced packaging technologies are great because, as someone said earlier, that I can design, my high power stuff on GaN. I don't, have to figure out a way to put that on CMOS. So it gives me that flexibility to use the exotic 3,5 compound materials where I really need that performance or that characteristic of that, particular material. And where I don't need it, I can throw in, something on a CMOS or an FPGA or something like that. So it's really, in aerospace and defense, to me, it's about that cost savings potential, and it's about that high mix flexibility of, designing the special sauce in the special materials only when necessary, and not having to, design everything on a monolithic substrate.
No, that's great. I'm going to let Brian steal, Pat Swami hat to ask his future question. So
Yeah, we like to ask our guests to look into their crystal ball a little bit. And I know, going back to the CHIPS program, one of the goals is to create what you said was, an ecosystem and a library of chiplets so that folks could go to Amazon and buy whatever function and chiplet they need. And so my question to you is, does that happen? And if it does happen, when? When do we have enough pieces out in the industry that we can actually start doing something feasible out in the open market?
Yeah, so it does happen. There's no doubt in my mind, based on conversations I've had with companies that are designing. Today they're building chiplets, but they're using them internally. But they are talking about, potentially sharing those chiplets. Now, will you see, two big CPU companies sharing chiplets across back and forth? I don't know, but there will be, because it's not a technology limitation, it's a business model limitation where Cadence, again, as an IP provider, is also looking at, how do we make our IP library available in chiplet form, right? So there is that's a business model. How do you license that? If you get my I license part of your chip because you're using part of my IP. So how do you license it? Who owns that product when it stops working? 5 chiplets from 5 different companies and the thing stops working. Who, just because chiplet from vendor A failed, maybe it was overheated by the chiplet from vendor B. So who, that whole, who owns what when things don't go well, needs to be sorted out. But I think a lot of progress is being made. There are discussions about things like chiplet configurators, where if you did have access to an IP library, you could go in, pick your library, say, I want, UCIe here, I want the UMI interface here, I want BOW here, I want a pin pitch of 35 microns. You basically configure all the blocks of IP you want. And there's reserved shuttle runs. So these companies that provide that IP, you go into their configurator, configure it. A month later, out spits, a known good chiplet, and you can start doing that. So we made a lot of progress with standards, which has helped. We're having discussions about, more frequently about potential of having chiplets available, broadly, as you said, from Amazon or wherever you might want to go. And so I think we're going to get there. If you ask me, give me a date, I'd say it's something I would say in the next 2 to 3 years. And I think a lot of that's going to be because of a lot of the CHIPS Act and the CHIPS Act. A lot of people in aerospace defense, realize that this is a limiting factor on moving to 3D HI, is the term they use, 3D heterogeneous integration. Is that availability of chiplets. And so with the CHIPS Act money coming in and these programs coming in, I think it's something that's going to happen in the next couple of years, where you will potentially have something like a chiplet configurator, or you'll just have a library of ready off the shelf sitting in a bin somewhere in a factory, kind of like PCBs, where you'll have all these different types of chiplets you'll come in. So it's going to happen, is what I believe. It has to happen for all of us to continue to make great products. So, and as I said, lots of people are having discussions about it, and it's not stalled out. I see a lot of progress in moving towards that sort of that consumer off the shelf availability of chiplets.
I guess, John, a question would be, so a bunch of my guys are interested in learning more about this. Where do they start? What's the next step for some of the engineers and maybe some of our listeners to go and, learn more about this? Where would he or she, kind of start learning more?
Well, there's a book on Amazon.com called 3D IC Trends. I'm one of the co-authors. You can learn a little bit there. There are a lot of universities that are, as you can imagine, I don't know if you've been involved with any DARPA programs, but they typically involve academia on the research side. So there are a lot of universities now that, because of course, as we know, the CHIPS Act, a big part of that, there are 4 components. One of the big components is workforce development. So there's a lot of effort, a lot of funding going underway with a lot of these companies that are participating in these U.S. government funded things to develop a workforce, working with universities, both undergrad kids as well as looking at junior colleges. A lot of this stuff you don't need a PhD to do. Place and route, for example. So there are efforts underway to start to bring the younger generation, to bring them into this market, because they don't, there aren't a lot of schools that teach, well, for that matter, there's not a lot of, universities that teach you what you need to do when the day you graduate as a double E, and, what your job is, and you're designing some huge ASIC. So there's progress in this area. There's always Google. You can go out there and Google a lot of these terms that we talked about, and there are a lot of articles that are written. Those of us in the packaging industry, we do have conferences. At this point, it's probably 8 or 10 conferences per year in North America. IMAP's Device Packaging Conference is a conference that's coming up here in the spring, which is a great opportunity to go and attend that conference. I don't work for them or anything. I'm just throwing that out there as an idea, but you can go to these conferences. There, people do talks on all the different, everything from material science to thermal analysis to mixed signal integration. You kind of pick your track and go along and follow those. And there's, the IMAPS events I talked about. There's ECTC. If you're more coming from the aerospace and defense side, go to GOMAC. If you've never been to GOMAC, GOMAC is really, jumped all in with this 3D HI. Tons of talks at GOMAC for those that want to learn a little bit more about this stuff.
Oh, great. Well, thank you. Appreciate it.
Great discussion, guys. Well, thanks, Brian, Sean, and John, for your insights in heterogeneous integration. If your listeners out there want to have any topics that we want to cover, just let us know. You can email me at phindle@mwjournal.com. Thanks for listening, and keep an eye out for our next episode planned for February 2024. Thanks for listening.